Welcome back to AlgoSTEM's AP Physics 1 free response series. This video will go over the third question in the 2018 free response. Question 3. The disk shown above spins about the axle at its center. The students' experiments reveal that while the disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. Part A. At time t equals 0, the disk has an initial counterclockwise, positive, angular velocity omega naught. The disk later comes to rest at time t equals t1. Part I. On the grid at left below, sketch a graph that could represent the disk's angular velocity as a function of time t from t equals 0 until the disk comes to rest at time t equals t1. Part II. On the grid at the right below, sketch the disk's angular acceleration as a function of time t from t equals 0 until the disk comes to rest at time t equals t1. So let's start off with what we know. We were originally at angular velocity omega naught. So we can put a point here. And it says that at time t equals t1, the disk later comes to rest. So we can put another point right here. Now let's see how we should connect the points. Looking back at the problem, the disk experiences a constant torque. And this is due to the friction between the axle. So we know that torque is equal to inertia times angular acceleration. Well, since friction imposes the rotating motion, the friction is negative, and thus the torque, which is due to the friction, is also negative. Since torque is inertia times angular acceleration, the angular acceleration is negative. Since the torque is constant, that means angular acceleration is constant and negative. So we can draw a line such as this. Now, if angular acceleration is negative and constant, that means the angular velocity would be a downward sloping line such as this. And if you don't know already, for an angular velocity versus time graph, the slope is angular acceleration. So the slope of this line is negative and constant, which makes sense with our angular acceleration, which is negative and constant. Part B. The magnitude of the frictional torque exerted on the disk is torque naught. Derive an equation for the rotational inertia I of the disk in terms of torque naught, omega naught, T1, and physical constants as appropriate. So we want some equation that solves for inertia and involves torque. Well, torque is equal to inertia times angular acceleration. Perfect. We can use this equation and rearrange it to say that the inertia is equal to torque naught divided by angular acceleration. So now we need to somehow describe angular acceleration in terms of omega naught and T1. So how should we go about this? Well, angular acceleration, angular velocity, and time are all interconnected. Recall that angular acceleration equals the change in angular velocity over the change in time. And these values were given, as shown here, and we can plug these in to solve for angular acceleration. In the end, angular acceleration is equal to negative omega naught divided by T1. And thus we can substitute this in back to our equation from here. So inertia equals torque naught divided by the quantity negative omega naught divided by time 1. And this all simplifies into torque naught T1 divided by negative omega naught. But since inertia can't be negative, we can just say inertia equals torque naught T1 divided by omega naught. Now you're wondering why this is the case. Well, since inertia is positive and angular acceleration is negative, when we multiply them together to solve for torque, we still end up with a negative torque, which is what we want. So that's why it works. Now for part C. In another experiment, the disk again has an initial positive angular velocity, omega naught at time t equals 0. At time t equals 1/2 t1, the student starts dripping oil on the contact surface between the axle and the disk to reduce the friction. As time passes, more and more oil reaches the contact surface, reducing the friction even further. Part I. On the grid at left below, sketch a graph that could represent the disk's angular velocity as a function of time from t equals 0 to t equals t1, which is the time at which the disk came to rest in part A. Part II. On the grid at right below, sketch the disk's angular acceleration as a function of time from t equals 0 to t equals t1. So it seems that from t equals 1/2 t1, the experiment deviates from earlier. So from time t equals 0 to time 1/2 t1, it will stay the same. So we can just replicate this portion from part A, as shown here. But now let's see how it changes from 1/2 t1. After 1/2 t1, there's oil, which would reduce the friction. So since friction is what causes the torque, reduced friction would reduce the torque. So torque would decrease over time. And if torque decreases over time, that means it would decrease in magnitude with a line such as this. That's why we can draw an upward sloping line from 1/2 t1 to t1. Now, we have angular acceleration from 1/2 t1 to t1. How would this translate over to angular velocity? Well, keep in mind that for the relationship between acceleration and velocity, if the acceleration decreases linearly, then angular velocity would decrease quadratically. So we can have an upward opening curve that's going downward like this. Now keep in mind this curve doesn't go to 0. The reason why is that oil reduces friction as time passes. So that means the torque becomes less and less. In the original scenario, friction would reduce the spinning to 0 at time t1, but that's because the friction stays constant and doesn't decrease. In this scenario, since it keeps decreasing over time, that means it'll spin for a longer duration. So at time t equals t1, it's non-zero and still has some angular velocity. And that would be it for part C. Part D. The student is trying to mathematically model the magnitude t of the torque exerted by the axle on the disk when the oil is present at times t is greater than 1/2 t1. The student writes down the following two equations, each of which includes a positive constant C1 or C2 with appropriate units. Which equation better mathematically models the experiment? Briefly explain why the equation selected is possible and why the other equation is not possible. So we're asked to take a look at the times after 1/2 t1. So that is when the oil starts to drip. We already established that as time passes, the oil will drip more and more, which decreases the torque more and more. We want some equation that would represent this. Let's phrase it into a paragraph. Torque decreases as time increases due to more oil being added to the axle. This decreases the friction, which is what causes the torque. The torque would decrease as well. Thus, the equation must have a decrease in torque as t increases. We see that in equation 2, torque and t are inversely related. So an increase in t decreases torque. That makes equation 2 the correct answer. So we can check off equation 2. But let's also take a look at equation 1 just for the sake of it. We see that if t here increases, that means this entire quantity here would increase. And that means as a whole, this t would increase as well. That means the torque and time are directly related, how an increase in time would increase torque. That's not the correct answer, as we want an increase in time would decrease torque. And as we said earlier, that would be equation 2. So this concludes the third question of the 2018 free response.